Okay, I'm surprised you're back. Yay. Yay, you. Okay, so last lecture I discussed the Joule heating law, which, as I said, is a mathematical expression that allows us to talk about how the temperature of the circuit path increases as a result of the fact that charges are moving through the wires. What I said basically was that as the charge carriers, remember the imaginary positive conventional charges, the conventional positive charges. Anyway, as the charge carriers move through the wire, there are occasional collisions of those charge carriers with the atoms that make up the wire. And so there's a loss of energy from the moving charges transferred to the atoms that make up the wire. Those wires absorb that energy, and we see macroscopically that absorbed energy in the form of heat. And the more heat energy, so-called thermal energy is the correct term, the more thermal energy that the wire absorbs, the higher the temperature of the wire becomes. As the temperature of the wire increases, the motion of the atoms that make up the wire likewise increase, which increases the probabilities that a collision will happen, which will then transfer more energy, raise the temperature more, and so the cycle continues. And the practical result of that is that the wire can get very, very hot. And so that led, as I said, to the mathematical expression, which I said was Joule heating law, and that's good. And then at the end of the lecture, I said, now what if we add a capacitor into the circuit along with the resistor? That will complicate things. Let's see how. So we'll have our battery, and I'm going to call it. I'm going to refer to its potential difference V rather than to its EMF. So let's just talk about potential difference. Remember, I mentioned before that most of the time the distinction between V and EMF is unimportant. So I'm going to go with E here, V, sorry. And so I'll have my battery there, and I'll have my resistor, again, whatever my device is that I'm trying to operate with my electric current. And I will put a capacitor there. And then this thing here is a switch. So in the case of something you might do in the lab, just some alligator clips, a battery, a light bulb, and then the switch really amounts to just connecting the alligator clips to the ends of the battery terminal. In the house, of course, the switch the switch closes the circuit. I forget. Sorry, I got distracted by an email, and I have no idea what I was saying. So let me just start over. So we'll assume that the capacitor, which is this thing here, is initially uncharged, and then we have the resistance. And so when we close the switch, that's when current will be able to start flowing. Let's talk about that a little bit. Let me describe it qualitatively, and then we'll start working our way towards quantitative calculations. Again, the question is, what current flows? What can we say about it? Well, obviously, before we close the circuit, nothing is going to happen. There's not a closed path. There's no way for the charges at the top of the battery to fall to the low potential of the bottom side of the battery. So with the switch open, nothing happens. Okay? So then we'll close the, so at t equals 0, the current is equal to 0. Okay? I can say that mathematically, by the way, by writing the current at t equals 0 is equal to 0, or I can even say the initial current is 0. So then I close the switch, and now current starts to flow. Now, again, qualitatively, what goes on? Well, the charge is going to flow, again, from high potential, it will spontaneously fall to low potential, except there's a capacitor in the way. Well, that's okay. We know about capacitors, so let's review it and see what happens. Uh, First of all, let me just real quick, imagine that this resistor were not there, if it was just a straight wire. We've talked about that. We've done that several times already. What happens is that, in fact, in physical reality, the positive side of the battery will attract negative charges from the top of the capacitor, and then so the top plate of the top plate of the capacitor loses negative charge. This is physical reality, by the way, not our convention. The top plate loses negative charges and thus becomes overall positively charged. The bottom plate, on the other hand, gains negative charges from the bottom of the battery, so the bottom of the battery becomes overall negative charge. The top becomes positively because it loses negative. The bottom becomes negative because it gains negative charges from the battery. And the result is the top plate is positive, the bottom plate is negative. They have equal and opposite charges, and that's the end of it. That's what happens in physical reality. In our imaginary world of the positive charge carriers being the things that do the moving, it's the mirror image of what I just said. Again, ignoring the resistor for the moment, the charges, and this, by the way, is how we're going to think about all this with the imaginary conventional charge carrier. In that model, positive conventional charges flow from the top of the battery over to the top plate of the capacitor plate, which gains positive charge, and so the top plate becomes positively charged. Meanwhile, positive charges fall from the higher potential of the bottom plate to the lower potential of the battery, so the bottom plate loses these positive conventional charges, thus becoming overall negative charge. Notice that the result is the same as what I described earlier a few moments ago as what happens in physical reality. The result is the same. The top plate becomes positively charged, the bottom plate becomes negatively charged, with the battery wired up as I've indicated here in this schematic. Okay, so we end up, but that process, that charging process takes time, as you know. We've done that before. There's a time constant associated with the capacitor, and the rate at which, maybe I haven't talked about that. Well, anyway, let me just say this. Again, we're doing qualitatively. The capacitor doesn't get to its full charge instantaneously. It takes time. Remember that? So there's that. Now, so that's all basically a review of how a capacitor works in the absence of the resistor. Now let's add the resistor in. The fact is, everything that I just said is unchanged, except the addition of the resistor reduces the current. Of course, that's what resistors do. That means simply that the number of charges that make it to the capacitor plate, to the top capacitor plate per second, is decreased compared to without the resistor. And therefore, the time to increase the capacitor is necessarily going to increase. In short, the more resistance you add to the circuit, the longer it takes the capacitor to charge. Okay? And you might be tempted to say, well, there's no resistor in the bottom half, and so the bottom half of the capacitor plate will discharge or will charge more quickly than the top plate will, and that turns out not to be true. I won't go into the details, but suffice to say that the draw of the bottom of the battery for positive charges to fall from the higher potential at the bottom plate to the bottom of the battery, that the positive charges would spontaneously fall from here to here. That's true, but there's also the effect of this increasingly positive plate here. So the bottom plate is getting more and more negative, but as it does, the increasingly positive plate tends to attract them back up, and that balances everything out, and the result is that the bottom plate charges at exactly the same rate as the top plate does, even when that resistor is in place. Okay, that said then, in short, the bottom line is that the capacitor and the way the capacitor charges is exactly the same with and without the resistor, except it simply takes more time for the charging process to happen. Okay, so the next step, of course, is to do a mathematical expression for this. And the fact is, deriving the equation that describes the current in the capacitor as a function of time is moderately complicated. Once again, it's a differential equation, which we're not going to do. So I'm simply going to hand you the result, although I'm going to actually hand you the result for a slightly different situation. Let's look at the next stage. This is charging a capacitor. Okay, let's look at the other side, which is discharging a capacitor. You'll remember, once the capacitor is charged, we can take the battery out of the circuit, capacitor, yeah. We can take the battery out of the circuit, attach the now charged capacitor, now energized capacitor, to the light bulb directly without the battery, and the light bulb will light because it's getting its energy, it's getting its current from the capacitor. That circuit looks like this. Okay. Still C, still R, still switch, no battery anymore. But also, by the way, the bottom plate is negatively charged, and the top plate is positively charged. Okay. The discharge process is much the same. Close the circuit. Now charge starts to flow, again, assuming positive charge carriers. Current starts to flow from the positive through the resistor, through the now closed switch. I should do this over here, by the way. Current flows from the top side of the battery through the light bulb, which lights, down to the positive plate, which becomes more and more positively charged. So we get a current that flows this way, and then this current flows that way. Okay, good. In this case, though, the current is flowing from the top plate, again through the light bulb, and again the light bulb lights. Why? Because there's a current through it, and all it knows is that a current went through it, so it lights. Okay? And this keeps on going until the charge imbalance that the capacitor started out with is no longer unbalanced. The two plates get exactly the same charge on them. The charge difference goes to zero. The electric field goes to zero. The electric potential difference goes to zero. The current goes to zero. The light bulb goes out, and you then go back and recharge it again and start everything over. All right. Once again, we can talk about the function, the mathematical function that describes how the current changes with time. And the current does change with time. How do I know? The light bulb starts out bright and gets dim. The brightness of the bulb is related to the current that's flowing through the bulb via the Joule heating law. Because the brightness of the bulb is calculated by I squared R. Okay? Cool. So power is an indication of how bright the bulb is. Double the current, the brightness increases by a factor of 4. But this current, like I said, is a function of time, and I'm not going to try to derive it. I'm just going to hand it to you. It turns out that the current for discharging the capacitor, now this is only for discharging, it doesn't work for charging the capacitor. But for discharging a capacitor, the current is a function of time, and it starts out here. Oh, I should be careful here. For when you charge the capacitor, which I was talking about over here, the initial current is 0. But when you're discharging the current, that's not true. The initial current is as large as it's ever going to be. Okay. I should be careful about this. Actually, I think now that I think about this out loud, I think this was wrong. So sorry about that. I'll have to think about that. I may correct that in a later correction. I think the initial current is also large here too, because after all, you hook this up and the light bulb is bright. So I think at t equals 0, so I'm sorry, mistake here. T equals 0, the current is a maximum. So I'll call that I0. Same thing here. So all right, the current then is I sub 0 times, get this, e to the minus e, that exponential thing, the exponential function, t over r times c. Okay, this is, if you remember your math, a decaying exponential function. This says that the current decreases as time goes on, and specifically it decreases like a decaying exponential. And the graph of such a thing the current on the vertical axis as a function of time, horizontal axis, looks like this. It starts out large and goes to 0. So it starts out here at I0, oops, and decreases to 0. But the closer it gets to 0, the more slowly the current decreases. Okay, so this is a measure. So there is a graph that looks very similar that corresponds to the power being output by the light bulb, which is primarily where the resistance is, and the power function looks very similar to this graph. Okay, which tells you that the light bulb starts out really bright and gets dim, but the dimmer it gets, the more time it takes for it to get any dimmer than that. Okay, so it decays like that, but you know, eventually it does. The current does go to 0, and the light bulb does go out. All right, so there's one more. You know, I think I was. Oh, here, I didn't. I'm having a little trouble with myself. I should have reviewed this before I made this recording, so I'll have to make another recording and correct it. But I'll either I'll make another recording or we'll talk in class about the charging current. I don't want to get distracted here because there's one more crucial idea that I want to give you. Let's take a look at this function here. Okay. So let's walk our way through these symbols. So capital I is the current that's flowing through the circuit, specifically the current that's flowing through the light bulb, causing the light bulb to light. Okay. T is time. I sub 0 is the initial current that flows at the instant we first close the switch, the instant we first connect the alligator clips, the instant we first flip on the lights, whatever. Okay. So the light bulb starts out really, really bright, right? So that means the current. That means that since the light bulb is really bright, that means it's putting out a lot of power. Since it's putting out a lot of power, and the resistance is presumably more or less constant, then the current, therefore, has to be large, or at least as large as it's ever going to be. The current. So, do you want to pause the recording just for a second? Okay, I have I've suddenly been invaded. The room I'm using now has to be used by somebody else, so I'm going to pause the recording here, or I'll stop the recording. We'll come back to this equation, and maybe I'll even fix all my errors before I make the next recording. Okay.